Good morning, everybody, and today we'll be talking about solutions. In particular, we'll be talking about physical properties, colligative properties, and Raoult's law. We'll begin with physical properties, but before we can do that, we have to define what a solution is. And a solution is a homogeneous mix of two or more substances, the lesser amount being the solute and the greater amount being the solvent. Now, at a given temperature, a certain amount of solvent can only hold so much solute. And this brings us into the topic of solubility, which can best be explained using a solubility curve. Now, as you can see here, at a given temperature, 20 degrees Celsius, we can use a curve to determine that 30 grams of solute can be dissolved in 100 grams of solvent. This is the solution saturation point. Now, if I were to add 50 grams of solute at the same temperature, then the solution is holding more than what it can hold at its saturation point. So at that point, the solution is supersaturated. If I were to add 20 grams of solute at that same temperature, then the solution is holding less than what it could at its saturation point. Therefore, the solution becomes undersaturated. Delta H of solution is equal to the summation of delta H1, H2, and H3. Delta H1 and H2 are both positive because it requires energy to break the solvent-solvent bonds and the solute-solute bonds, causing delta H1 and H2 to be both positive. Delta H3 would be negative because the formation of bonds between the solvent and the solute molecules would release energy, causing delta H to be negative. Now, if the solvent-solvent bonds or the solute-solute bonds are extremely strong, then it would require more energy to break them, causing delta H1 or delta H2 to be more positive, causing delta H of solution to be more positive. Same thing with delta H of 3. If the solute-solvent bonds are extremely strong, then it would release more energy when it forms, causing delta H3 to be more negative, causing delta H of solution to be more negative. So as we move forward, we need to talk about concentration units. Now, there's only two that you really need to be concerned about because I'm pretty sure we know how to do percent by mass and mole fraction. So the only two that you need to be concerned about, or concerned about not mixing up, is molarity versus molality. Molarity, big M, is moles of solute over liters of solution. Moles over liters. Something that we've all seen before. But we have to be careful not to mix it up with molality, which is little m. Moles of solute over mass of solvent in kilograms. You have to make sure it's in kilograms, kids, otherwise your units will be all wrong. Now we'll be discussing colligative properties, which are properties that are solely dependent on the number of solute particles inside the solution. This is related to our Van 't Hoff factor or I factor. I factor represents how many individual particles a compound will form in a solution. In the case of calcium chloride, it will ionize into 3 individual ions, and so its Van 't Hoff factor will be 3. For calcium chloride, it will ionize into 2 separate particles, so its I factor will be 2. For your molecular and organic compounds, its I factor would be 1 because it will not dissociate or break apart or anything like that. I factor will be used in the first two colligative properties, which are boiling point elevation and freezing point depression. To calculate your new boiling points, you would have to calculate your delta T by multiplying K by I by M. K being a constant, I being your Van 't Hoff factor, and M being your molality, which you'll remember is your moles of solute over kilograms of solvent. After delta T has been calculated, you would add it back to your original boiling point to get your elevated boiling point. It's the same concept for your freezing point depression, except you would take the delta T that was calculated and then subtract it from the original. Our next colligative property is osmotic pressure, and it's obviously related to osmosis. As you can see here on the right of the semipermeable membrane, the water is full of solute, so the water on the left of the membrane will move toward the right to dilute it. And osmotic pressure is the pressure required to stop osmosis. The equation for that is P equals mRT, or MERT, M being your molarity, R being your gas constant, and T being your temperature in Kelvin. Our next colligative property will be dealing with vapor pressure and Raoult's law. As you can see here, the equation for the total pressure is the mole fraction of your first component times the initial vapor pressure of your first component. And you can add as many of these components as you need for the problem. When we're dealing with Raoult's law, one would consider deviations. In the middle is your ideal graph. If there is positive deviation, it will look like this, and this is because of the components within the solution repelling each other, causing causing an increase in vapor pressure, essentially. And over here is a negative deviation, in which the components within the solution are actually interacting and attracting each other, causing a decrease in vapor pressure. So in this example problem, George was cooking spaghetti, so he boiled 4.1 kilograms of water and added 58 grams of salt, which I assume is table salt or sodium chloride, and then boiled it again. It's asking for the temperature of the boiling salt water, so it's basically a boiling point elevation problem. So the delta T is equal to K-IM. So it gives you K, of the K of water being 0.52. Van 't Hoff factor, or the I factor, had to be 2, since sodium chloride would form 2 ions in solution. And then had to calculate molality. So I took the 58 grams of sodium chloride and then converted that to moles, which was 0.99 moles of sodium chloride. And then put that over 4.01 kilograms of water and got 0.25 molal. After plugging everything in and multiplying, the delta T equaled 0.26 degrees Celsius. I added that to the original boiling temperature of water, which was 100 degrees Celsius, and got 100.26 degrees Celsius.